Okay, welcome everybody. Uh, for me, it's a pleasure to introduce Fabrice or Fabricio Gamboa from the University of Toulouse. Now he's at the University of Medellin uh, for a couple of months. And he is one of the experts in statistics, well known all over the world, even in Venezuela. So, well, Fabricio, the floor is yours.
Okay, thank you very much, Wilfredo. So I will talk you first of all, good afternoon, everyone, and I will try to talk you about an interesting connection between probability and a kind of Szego theorem. It's a very long collaboration with almost a 10-year collaboration with Jan Nagel, which is like now a professor at Dortmund University, and Alain Rouault, which is now still professor at Versailles University. Thank you very much for the invitation of this colloquium. So, first of all, I will really thanks my friend, my marble friend Wilfredo, for the invitation. Actually, I am on the road to go to Minneapolis for the SIAM conference, and it is really a pleasure to spend some time here with you. So, to begin with, I will give some bibliography related to the work I will give you. So actually, in all these spectral theories around the Szego theorems and all this generalization, there's a real very good book from Barry Simon, which appeared now 15 years ago. All these things really, I really like this book on orthogonal polynomial with a big synthesis on many things on orthogonal polynomial. That is the second volume. It's quite complicated and complete. And okay, we will make a connection between all these things in spectral theory and the large deviation theory on random matrices. This book is a very good synthesis on the subject. Okay, so just some papers about
Hola, estoy en una charla de matemáticas.
the the
Sí,
the this work. Okay, so this work began early, like 10 years ago, in which we discover the connection between this Szego theorem. I will recap soonly, and some large deviation properties of some random measure built by random matrices. Okay, so in a series of paper, okay, we begin with this paper, and then okay, the method I will try to give you to explain you have been developed in many directions. Okay, but staying maybe or as we are people working in I am mainly working in statistics, and Alain and Jan are much more working in probability. This is much more written in terms of probability. And so Simon and Zeytouni use the method we first developed in this paper and try to transmit how it works for people from spectral theory. And there is a much more analytic presentation of what we have done in this paper. And then they use the technique in order to obtain other Szego theorem. Okay? So more or less, I will explain by hand what is our contribution. That is, generally speaking, in algebra, one say E equal B it's more or less tautology. That is, if something is equal to something else, oh, okay, it's fine, it's easy. In analysis, okay, generally to show an equality, usually sometimes it's useful to show the two inequalities, these two inequalities, okay? But when you do that, generally you have different reasons, very different arguments to show the upper bound and the lower bound, and you don't really understand why the relation hold. So our main contribution is that we more or less we have gave a probabilistic machinery in order to establish complicated equality in spectral theory. And more or less, the main idea is a very simple idea. That is, if you know large deviation, that is the large deviation is describing the exponential behavior of some object which is concentrating on something. And this is describing how this law of large number happens in terms of a rate function. And it's appeared that the rate function of a large deviation principle is unique, meaning that if you can show a large deviation principle for some object which is concentrating, and that you obtain that the rate function has two expressions, this implies directly that the two objects are equal. So our main argument for all this work is to take some random object, which I will try to describe, which is a random measure built on random matrices, and to show that this object satisfies a large deviation principle in two ways. Okay, actually in two encoding. That is, as we will work with a random measure, we will encode this random measure either as a random measure supported by some set, but also with some kind of coefficient related to its orthogonal polynomial. And that's the link, more or less. Okay. So to begin with, I will recall some important quantities we have to deal with in this work. So first, the first one is quite classical. Okay, generally it's called the crescentropy, or maybe the sign is not this one, but as a statistician, I present that as the Kullback labeler divergence or information. Okay, this quantity is quite central in statistics for many problems as asymptotic statistics, or even for a test and so on. And it is a really important object in the theory of large deviation. Okay, this is indeed a rate function for the classical empirical measure of IIDs on an ID sample. Okay, it is a quantity which remain non-negative, and which is quite classical. Okay, so now let's give you some refreshing on orthogonal polynomial, and begin with orthogonal polynomial on the circle. When you have a probability measure on a circle, you can build an orthogonal a sequence of orthogonal polynomial associated to this measure. Okay, there is many ways to normalize it. Here we will normalize it as monic polynomial, meaning that the term of higher degree is that is the coefficient in the term of higher degree is 1. And of course, because they are orthogonal polynomial, once I have defined the normalization, it just means that when you see the L2 scalar product one-ish when you take two of these polynomials. The very interesting things with that I discover, I didn't know many things on orthogonal polynomial, is that Okay, you can apply the general if you want to know to build a sequence of orthogonal polynomial, you can apply the so-called Gram-Schmidt process, in which, okay, to compute the new one, you just make you enter on the new monomial and you make a regression with the old one. Okay, you regress on the old one, and it's happened that for polynomial on the circle, and we will see what's going on for real polynomial on the line. When you do this regression, this involves only one polynomial of the only one previous orthogonal polynomial. That is, you can compute the next monic polynomial by this recursion. Okay, where this seems to be complicated, but it's just the same polynomial, and you are reversing the coefficient. That is, now in this, the first coefficient was the one of the highest degree before, and so on. Okay, and this recursion, in which to compute the next one, you have to make some regression, functional regression on just the last one. There appear a coefficient which is very important in many theory. For instance, in statistics, very important coefficient that allowed you to make some forecasts, for example, for Gaussian series. And this coefficient is called the Verblowski coefficient, but it actually has many names in probability and statistics. In statistics, people are calling this coefficient the canonical moments, following the theory of student and death, for example, or a reflection coefficient. Okay, so the main things will be related to this sequence of numbers. So I will recall the Szego Theorem, the classical Szego Theorem. What does say the classical theorem in the term of the Kullback information is that taking a measure, mu being a measure on the circle, then there is two expressions to compute this Kullback information. Recall that this Kullback information was this logarithm, okay? So the first expression is related to this integral. And the fact is that you can compute this quantity by the way of the coefficient of this Verblowski coefficient appearing in the regression to compute the orthogonal polynomial by the way of this formula. And this formula always holds, meaning that if this quantity is infinity, that's it, meaning that this quantity is also infinity. Okay, that is, these two quantities always coincide. Okay, even if here you have not summability. And just one comment is that in this formula, you see, is the Kullback information in some sense appear not in the classical way of large deviation. That is, the argument is the second measure, probability measure. Classically in large deviation, when you are looking at Szego Theorem, which is giving the large deviation for the empirical measure, the argument in the rate function is the first one. Here you have fixed the first argument to be the normalized Lebesgue measure. Okay? So, yes?
Yeah. Fabrice,
yes?
So you have the mu, you have the family of orthogonal polynomials with
Yes.
respect to mu.
Yes.
And then you compute this alpha.
Yes.
Okay. So all that is related with mu. So I still don't.
Yes.
What is the
so
lambda?
Here
But what is the
lambda is fixed, is the Lebesgue measure, is the reference measure.
But the right hand side does not depend on lambda. Depend only on mu.
The right hand side depends on lambda indirectly, because if mu is absolutely continuous with lambda, Okay, it's a very deep result because actually you're right. Here, lambda is not obvious, but the fact that this summation gives you something finite, in one sense, you can read a property in that your entropy is finite. Okay, this is very deep. Yes, you're right. It is hidden in one sense. That is, it's quite interesting because actually this formula give you many information on mu and its property, because this implies in particular that this callback information is finite if this one is finite, and conversely. Okay. So this is the starting point. That is maybe you met this Szego Theorem in another way. That is, I wrote it to see that here you have a callback information, but generally it's appear to be the integral of the logarithm. But it's the same thing. Okay, after you have to put the normalization, and there is these two quantity which are non-negative. Okay. So this is the case of the Szego Theorem, which is quite old. And the classical proof for this theorem, there are many classical proofs. One is quite easy, is to show that the formula hold for a rational function. That is more precisely for inverse of positive polynomial of the exponential, that is of the trigonometric argument. And you show that this formula hold because for the inverse of positive polynomial, that is the coefficient R1 for sufficiently big n. Okay, so the series is just a sum. So you can just by complex analysis for the inverse of positive trigonometric polynomial, you can show this formula quite easily. It's just some complex analysis, and then there is a very nice extension just by density. That is, you approximate the measure by the way of this inverse of a positive trigonometric polynomial. Okay, this is the very classical proof, and we will see that there is another proof. Okay, let's now turn to a more generalized situation. Okay, I thought about the case of a measure which is supported by the circle. Actually, you can more or less generalize the picture on R. Okay, when you are dealing with R, okay, of course you have to assume that if you want to make some orthogonal polynomial, that the measure you are dealing with, the probability measure you are dealing with, as all these moment finites. Okay, and so you can do the same thing. That is, you can build the orthogonal polynomial. This way, I will normalize it to be in L2. There is any time with the polynomial, either you choose to normalize it by the way of the most the highest degree to be 1, the coefficient to, or to be normalized in L2. Okay, and when you do exactly the same job that we have done for the circle, that is, you are doing just this a very, very simple Gram-Schmidt process, it's appeared that now if you want to compute the new one, it's appeared to be a regression of the two last one. Okay, and this coefficient, in the case of the circle, we have a complex coefficient, which was this Verbludsky coefficient. And here, more or less, we play the same role of the coefficient. The Verbludsky coefficient are this coefficient, this sequence E and B, which are classically called the Jacobi coefficient, in which the coefficient E is positive and B could be any real. Okay, so this the demonstration of that is the same as in the circle case. It's not difficult. It's just more or less the main thing is that the monomial x power n plus 1 can be reproduced just by taking x power n multiplied by x. It's just a reproduction property. When you do you use that, you can obtain this formula. Okay. A little bit more involved is that in the case of a probability measure on the half line, you can reparameterize these two coefficients by just one coefficient. That is, these two sequence depends only on this sequence Z. Okay, and then something much more precise, when your measure is supported on 0, 1, okay, you can push, of course, 0, 1 on the circle. Okay, you can push it on the circle by this transform, and then so that you have a measure on the circle, you can push your measure on 0, 1 to be a measure on the circle, and then the coefficient A and B can be expressed by the way of the Verblunski coefficient, which are in this case real. Okay, more or less, this is the global picture. Just one word about that is that there is also a kind of other Verblunski coefficient, which are not exactly this one, which are quite useful in statistics and are called canonical moments, and are very, very useful for many problems in statistics and in analysis and also in optimization. Okay, so more or less you have this picture, this general picture. Okay, this is the real line, this is the half line, and this is the more or less the interval. And in the case of the interval, you can relate this by a classical pushing on the circle. Okay, so as society, remember that on the circle, as Wilfredo pointed out, there were on the left side of the equality, there were this Lebesgue measure. That is something. There is something which is hidden, which is some corresponding to this frame, which is an equilibrium measure. Okay, and let's have a look to what can be the equilibrium measure. So we have three very particular probability in this three frame. That is for the real line. There is this very particular measure which will play the same role as the Lebesgue measure will play, which is the semicircle law. Okay, semicircle law, which is more or less it's a beta distribution with parameter is parameter 3/2, something like that. But okay, it's not the classical beta. You have to take it on -2, but more or less is a beta distribution. Okay, the semicircle law, and it is a quite interesting distribution because it mainly appear many times in spectral theory as some extrema, and also in random matrix theory as the limit of spectral measure of eigenvalues in many examples. Okay, and he has the very interesting particularity is that the Jacobi coefficient are all 1 for A and 0 for B. Okay, this is for the case of the real line. Now, in the case of the interval, the half line, there is this so-called Pastur-Marchenko distribution, which appear also to be the limit distribution of the random eigenvalues for more or less for Wishart, general Wishart matricial distribution. If you take you take the eigenvalues, you make the good normalization, and then you will have this as limit for the empirical measure of the eigenvalues. Okay, and of course the tau will depend on the ratio of the column number and the line number. And this corresponds to a very special sequence of Z, which are this one, constant for this term and constant for this term. Okay? And the third interesting distribution are appearing in many problems related to random graph, are the so-called Kesten-Mackey distribution. And they appear in random matrix theory as the limit distribution for the Jacobi ensemble. More or less, the three main ensemble of distribution of random matrix are the Gaussian for the line, the second one for positive are the Wishart, and here more or less this is generalization of beta distribution, but in the matrix for matricial. Okay, more or less the density. The main picture is that you have the three main ensemble of matrices. The first one are the Gaussian. The second one are Wishart, which look like gamma. That is, you can more or less the density can be written more or less as a gamma in terms of the matrix, and here it's more or less a ratio of gamma. Like this is ratio no, but you have to inverse a matrix, and it is the equivalent of the beta distribution, but in the matricial case. Okay, and so here you can make also the computation. There is closed form for all these coefficients. That is, you can compute either the Verblutsky coefficient for this distribution, or also the E and B, and so on. Okay, but it's not very important. So now you remember on the circle we had this very nice Szego Theorem, which is relating the Kullback information, the reverse Kullback information. That is the first argument is the Lebesgue measure to a generic measure. Is this Kullback information is related to the infinite sum of the logarithm of 1 minus the square of the Verblutsky coefficient. So the question is now, what's going on the line? Okay, do we have this kind of theorem on the line relating some quantities, okay, and the coefficient E and B, okay, and we had to wait up to it was a paper of the early 2000 in which Philip and Simon show this formula. It was not written in this way, but just have a look now to this formula. Okay, this is the information term. Okay, now we remember that in the case of the circle here it was the Lebesgue measure. Now the equilibrium measure, that is the measure replacing the probability measure replacing the Lebesgue measure, is the semicircle. Okay, that was the one which was this beta on minus 2,2. Here we recognize something which is not exactly the same as in the circle, but something that is related to the Jacobi coefficient. Okay, that is, before we had only minus logarithm of 1 minus the modulus of the Verblutsky coefficient. Now you have all these guys. Okay. And the difficulty to show this formula is that appears something here that was not present in the Szego theorem. And what is this? Okay, this function is given by this complicated things. That is, you have to integrate this guy. This is a given function. And who are these guys? Lambda n plus and lambda n1. minus. Okay, this is, wait, remember that mu is quite general. It's a probability measure on R now. Okay, so you have a contribution of the measure on the part which is here. Okay, the contribution of the, and you have further, you have a contribution of the point, the pure point of the measure mu, that is here, the lambda n plus, are supported point, discrete supported point, which are greater than 2. Okay, you remember that this measure is supported on minus 2, 2. Sorry. This measure is supported on minus 2, 2. Okay? So these are just the contribution in terms of just the pure mass of mu, which are greater than 2, and these one are the one which are lesser than 2. Okay? And you see this equality every time holds, is the same. That is, for example, is here mu has a bigger support than minus, that is the absolute continued part is greater than minus 2, 2, this will be plus infinity, okay? Because you will have zeros in the density, okay? And here, that means that in order that this thing is finite, that is, this thing is finite, you have to work with a measure which is density, that is the absolute continuous part. It is between minus 2 and 2, but you can allow pure mass which are away from this interval minus 2, 2. Okay, so this formula tell you that in case you take a measure which has an absolute continuous part which is greater than minus 2, 2, this theory will be divergent. Okay, because these two terms always coincide for any measure mu on R, any probability measure on R. Okay, this is clear, this formula. This is more or less a Szego theorem in which you have the main part is as before, that is, you are relating the Kullback information to some series where the Jacobi coefficient appears, but you can allow to have a part which is not absolutely continuous, but in which you have to sum this series, where I didn't say, but n plus and n minus should be in order that it converges to be finite. Okay, is it clear? Is it clear? Yes? Yes? Okay. So this formula, you see from the first Szego theorem to this generalization on R, mainly because this is very difficult to show because of that. That is in generality. If you take mu, which is supported by minus 2 and 2, and which is regular, it's quite easy. That is, no, it's not quite easy, but there is trick in order to show this formula. The general case is much more involved. It's very difficult to show that by pure analysis argument, and they achieved to do that in the 2004. It's a big paper of Philip and Simon, I think, in Invenciones. Okay, a very big paper. Anytime I try to read this paper at the fifth page, I give up because it's too complicated for me. Very complicated analysis, and the fact is that I will explain you, but we recover all this formula by the way of large deviation. It was our first work to show that this formula, which is very, if you use analytical tools, is very difficult to show. With a probabilistic argument, I will not say it's obvious, but it's quite easy. That is the difficult part for the probability proof. It's also in this guy. That is, this part is very easy, but to show that this part appears is quite difficult because it's related also I will explain later the random object we will deal with, but more or less the random object is some spectral measure, random spectral measure, which mainly concentrate on -2,2, okay? But there is some outliers. And in terms of probability, that is, you will have some outliers away from -2,2. And technically, the treatment of this, the asymptotic behavior of this outlier is quite difficult. It's quite technical, not difficult, but quite technical. Okay. So before explaining that was so, this paper is very famous. This paper of Philip and Simon. Before explaining the probability argument, I will just give you some rule we show easily using this technique. The first one we show, because they will generalize. We have generalized in many ways, but more or less we obtain some rule for the two other models, and these some rule were not known. That is we obtain some rules for the Wishart case and for the Jacobi case. Okay, and more or less in the Wishart case, that is when the equilibrium distribution is the Pascoe-Marchenko distribution. Okay, more or less you have the same picture that you have in the case of the Killit-Simon. That is, you have this Kullback information is related to the coefficient zeta with some function which is not exactly the same. Okay, which is not exactly the same as before. Okay, and you have the contribution of the outlier by the way of this function. Okay, more or less you have the same picture as you have for the real line, for the half line, but you have a new sum rules, and these new sum rules involve the Pascoe-Marchenko distribution and this coefficient that allows you to parameterize the Jacobi coefficient, the general Jacobi coefficient. And in the case of the beta distribution, that is the Kesten-Mackey, you have a family of sum rules, okay, in which you have to change the function here, but anytime it's beginning by the same thing, the Kullback information, the reverse Kullback information with respect to the equilibrium measure. And you can express that by the way of some function. I don't know if I put this function. Is not interesting to have the details, much more the spirit, which is interesting, and to see that the technique we have proposed is a machinery to obtain this kind of formula. Okay, but each time, more or less, you see this. Okay, I give the H1 and H2. Okay, and so the Szego Theorem appears to be a special case. It's not very interesting to know the explicitly this function, but more or less the general picture is that you have more or less a reverse Kullback information with respect to some equilibrium measure. Okay, on this side you have some function of the coefficient describing the recursion of the orthogonal polynomial associated to mu, and here you have something which is quite unusual and is related to the pure masses of the measure mu. Okay, this is as before. Here are the outlier of the measure mu, that is the one which are not in the limiting support of this distribution. This is clear? Okay. And now the question is, okay, we try to give you the spirit of this machinery in which you more or less, we will have a random object, and this random object will concentrate to some measure. Actually, in each case, it will concentrate on the equilibrium measure, and it will concentrate exponentially fast. And the way it's converging exponentially is called the rate function, and we will identify the rate function in two ways. And because of the uniqueness of the rate function, we will obtain directly the equality. So let's turn to the object we are dealing with. Okay, in spectral theory, or even in just infinite dimension, when you have an operator, you can define a spectral measure which is defined through his moment. Okay, that is, you can define a probability distribution just by this equality. Okay, so we will mainly write just on a circle or on air, and we will take with generally with self-adjoint or Hermitian matrices. So the picture is the following: you randomize, you will consider this measure, but this measure will be constructed by the way of a sequence of random matrices. Okay, that is, if I randomize now, if I take a random matrices, I can define this measure to be mu n. Okay, okay. And what is this, more or less this mu n typically, how it is? It is a pure mass, it's a pure mass measure, which is supported by the eigenvalue of the matrix Emin, right? This is supported by the eigenvalues of Emin. And here you have a positive weight that can be computed by this vector. Okay, so you can now, okay, this is, you see the way that is our object, our random object is mainly this measure, which is built using more or less the eigenvalue of the distribution of the matrix distribution and this random weight. Okay, and with this, of course, with this measure, you can make some orthogonalization of polynomial related to this random measure. You have random orthogonal polynomials, and so you can define this sequence, either the Jacobi sequence or the Verbluski sequence. Okay, this is the main picture. And what else? What is the idea? You will characterize the large deviation in two ways. That is, generally, for the classical matrix ensemble, this matrix will converge to the corresponding probability measure. That is, in the Gaussian case, is the semicircle. In the Wishart case, the Pastur-Marchenko. And in the beta case, it is this Kesten-Mackey distribution. Okay, so this measure converge. Then you have to study the large deviation, and so to study the large deviation, you see that here you encode this measure in two ways. First way is the classical one that you are describing how if you want to integrate with relative with this measure, if you want to integrate with this measure, you just have to take this delta Dirac and take the sum. Okay, here you are describing how is the measure by the way of integration. But there is a second way to describe the measure by the way of the coefficient. Okay, so the two way you are describing the measure, and you can study its asymptotics, is either to see directly as a measure, you have a random measure, and what's going on for the location and what's going on for the weights. And you have a second way to study the asymptotic of the measure, is how the coefficient, either, for example, the Jacobi coefficient are converging. Okay? If you can do that, you can characterize the large deviation property of mu n by the way of that, either this one and this one, then you will have that these two functions will be equal. This is because of the uniqueness of the large deviation principle, in the large deviation principle. Okay? So just one parenthesis is that generally in the paradigm of random matrices, people are working with this guy. Okay, that means they are taking the empirical distribution, the classical empirical distribution, supported by the eigenvalues and normalized by 1 over n. This is not our measure. In our measure, there is two random ingredients, not only the eigenvalues, but also these random weights. Okay, these random weights are summing to 1, and they are on the simplex and they are non-negative. Okay, and that is just to give you the spirit in the case which is much classical, that is, which is the Gaussian case, how it works. So in this case, you are randomizing the matrix by the way of this distribution. Okay, this is the Gaussian distribution. And there is a very, very intriguing and interesting thing is that when you are randomizing the matrix by the way of the Gaussian distribution, if you take the distribution of the Jacobi coefficient, they are independent. Okay, the sequence of Jacobi coefficient is well defined for the measure I gave up to n. And to n minus 1, there is a shift in the definition. And all these random variables are independent. It's quite magic. It's quite magic for the Gaussian case that the Jacobi coefficients are all independent, and we know precisely their distribution. And if you have a look to their distribution, you see, for example, for the B, this is nothing more than a Gaussian distribution, which is concentrating with the variance going to 0 at rate 1 over n. And the same, okay, it's much more intricate, but for the coefficient A, you have more or less the same things. And this explains easily, this is quite intuitive, that when you look at the large deviation on the coefficient side, it's quite easy. Because as you have independent coefficient, you will have some, and you know exactly how it concentrated. And here what you are reading is nothing more that the rate of the large deviation rate for the Gaussian part, okay? And this is the large deviation, the classical large deviation rate for the gamma part, okay? You can read it here that this is some logarithm of the, just is nothing more than the normalized logarithm of the density of the gamma. And here is the logarithm of the Gaussian, okay? So for actually for the Kilip, the Kilip-Simon sum rules, the left part is quite easy to obtain because you have, by this theorem, you have independence. And so by n, you can compute the large deviation of this sequence. It's quite easy because they are independent. That give you directly that the rate function are this sum. Okay. On the other hand, for the measure side, for the Kullback side, say the left side, it's a little bit complicated, but not so. That is, you can write on this spectral measure, as we saw, as a weight multiplied by delta Dirac in the eigenvalues. And for the model I present, the density of the eigenvalue is very well known. That is, generally for this kind of matrices, that is, if you take this Gibbs measure on matrices with some potential, okay, for example, in the Gaussian case, this is this potential, the eigenvalue distribution is well known, and because the density is depending only on this term, that is the trace of the potential, this weight, the distribution of this weight are completely known. These are uniformly distributed on the simplex, okay? And they are independent because of this form. They are independent from the eigenvalues. Okay, so the measure the structure of the measure is not so complicated because here you have independence between the random weights, which is just uniformly distributed on the simplex, and the gain value in which you know exactly the distribution. So when you combine that, you can show that is for this general family of random matrices, that is when given a potential, then you can show it's a little bit more involved than the proof for the right part, that is the part in the Gaussian case for the coefficient. You can show that the random measure satisfies this large deviation property, in which there is this reverse Kullback information appearing, and the outliers, the one which are away from the support of the equilibrium measure. Okay, that is the pure point mass of the measure mu, which is away from the limiting support. Okay, so the main difficulty to show that is not that. That is this part is very easy because it's more or less, if you see the structure, I come back to the structure. That is what's happened is that this, maybe you know that is the classical empirical spectral distribution is converging very fast to the equilibrium measure, very, very fast. The convergence rate in large deviation is not n but n squared. Okay, for if you replace this, you just take 1 over n and don't put this random weight. 1 over n delta lambda is converging at rate n2, n squared, in terms of large deviation, meaning that when you want to study the large deviation of this guy, more or less the randomness comes from here. Okay, the randomness come here. That is, you have to study what is the behavior of the more or less the uniform distribution of the simplex, and this is going to 0 with rate which is given by the more or less the exponential distribution. So this part is quite easy to obtain because the support of the measure is converging very fast to the equilibrium distribution, and further, you know exactly the behavior of the weights. Okay, but the difficult part is for the pure mass which are away from the limiting support. That is, you have to make a very, very refined argument about what's going on for these points which are away from the limiting supports. And this rate function appear to be some rate function of extreme eigenvalues in random matrix paradigm. That is, this is the rate function if you study the extreme value of the extreme eigenvalues in this random matrix paradigm, then this is the rate function of this extreme eigenvalues. Okay, so here for this part, the difficult part and the technical part is just here. Okay, and so what's going on, if I recap, is that from the left part, okay, we have a general large deviation principle. That is, you see, here it's quite general. That is, we have a general large deviation principle for all these families of random matrices, which are the general potential. But on the other side, the case in which you can specify exactly the distribution of the coefficient, they are not so numerous. Okay, mainly we have treated the case, the 3 cases I described, in which there is some magic distribution theorem in which you can really write down the distribution of this coefficient. But in general, this is not so obvious. Okay, so I just recap to end more or less what is the method for to get some rules from our probabilistic arguments. You just take from the spectral side, you can have a general potential. This includes the three classical case, and then from this side we have a general large deviation principle, and we have identified the rate function. From the other side, it's not so obvious. That is for the coefficient side in the three classical ensemble. You can characterize the distribution of the coefficient side, but in general, the distribution is very involved. That is, we have made some progress. In some case, we know we were able to compute this distribution, for example, for the case of block matrices, but in general, it's very involved. And I will maybe stop there. And thank you very much for your attention. And if you have any question, they are welcome. Thank you very much. Thank you, Melanie. Wilfredo is frozen. Can you hear me?
Hi.
Okay.
Any question? No questions? Well, let's send the speaker again. Then thank you for everybody to come, and well, I will publish the recording as soon as they are available. Okay.
I have a question.
Carlos. Okay, go ahead.
Okay. Oh, very hard stuff, Mr. Fabrice Gamboa. It's not too easy at all. So I hope I could understand something about all that thing you are talking. I have some matter of comparison with the size of the AK and BK for the order of the convergence of the recursion equation that appear all along the talk. I don't found that, perhaps you said it, but I can found the calculation of the exact size in order to guarantee the convergence of the iterative equation.
That is, you mean for the side, you mean in here, for example, the conversions of this part.
Exactly. This kind of calculation. For example, when you have the sum base under K or multiplied by under mean and a half plus a K times the function that you later call G. It's not too clear to me to understand the conversion, this kind of equation.
No, that is the conversion is not obvious, but what you know is if this one is finite, for example, if you don't have outlier in the measure mu, imagine that mu has the same support as this one, and if this is finite, this implies that this is finite. Okay. Is the only answer I can do. Okay, that is what is interesting is that in all this formula, if one side is finite, then the other is also finite. So that can give you, and also I didn't bold this point because it was really your question is really interesting. Is much more what Simon generally present. That is Simon, and when they present the sum rules, that is the analytic way to obtain this. they say that it's very interesting because that give you exactly what is your question. That give you some criteria in order that if you can warrant that this is finite, it will be finite. So
Okay.
you warrant by the way of the callback information, you are warranting by the way of the callback information that this series in which the coefficient you are computing are very complicated. You cannot, generally, you don't have closed expression. It's just a
Okay.
theoretical tool. But these coefficients are very important in spectral theory.
Sure.
And
Sure.
so this kind of formula are very important to answer your question. That is, the
Okay.
convergence of the right side can be done giving a sufficient condition on the left side.
Yeah. Okay. Thank you very much.
Thank you.
Congratulations.
Thank you. Thank you.
Please, could you put back again the Szego's formula?
The Szegos one. Okay. So the Szegos one, there is, you can show it. It's very in your frame. That is, it's quite simple to show that with the matrix frame is what they have done as example in the paper of Simon and Zeytouni. They take, because here to show this formula, you just take the R measure on the unitary. If you take the R measure on the unitary and you take the spectral measure I mentioned, that it will be, the eigenvalues will be on the circle, right? For the unitary ensemble, the R measure on you randomize the matrix like that, and directly these coefficients are also independent. And so you obtain directly that. For the case of the Szego theorem, okay, I put that in the very general case 10 Mackey, but to begin with, if you have a look at the paper of Zeytouni and Barry Simon that want to explain how we work, our method, they take this example. And by hand, they are showing the large deviation of the measure and the large deviation of the coefficient, which are independent. It's a good starting point to have the proof of the Szego theorem by the way of this random measure. Okay, in the paper of Simon and Zeytouni.
Okay, yeah. Any other question or comment? Okay, thank you, Fabrice, for
Thank
your.
you. Thank you for the invitation. Thank you so much. It was nice.
And I will, as soon as I have the recording, I will publish on YouTube, and you will get the recording too. Okay. Thank you everybody for coming, and see you later, alligator.
Thank you.
Thank you.
Bye.
Thank you very much for the invitation.
Bye.
Enjoy.
Thank you.
Bye. Thank you.
Luis, no
Hola,
hiciste
Luis.
mi pregunta, Luis.
Hola. ¿Cómo estás? Ricardo, Enrico, estás mute.
Ah, Luis está dormido. Tiene un hoodie. ¿Tiene hoodie?
Sí, está. Parecía Batman.
No,
Árabe, no.
Tira piedra. Oye, qué bonito trabajo, pero bien complicado los cálculos del trabajo, porque
Sí.
la función que convenza esa X